Hello and welcome to our part 3 ANOVA chapter video. We're going to get right into continuing where we left off, where ANOVA and the t-test. So once again, when we're talking about ANOVA, we're talking about most of the time 3 or more groups. If you're doing just 2 or more groups, you can use ANOVA or a t-test. For groups or of 2 and you're using ANOVA, you're going to use the equivalent to the equal variance pooled t-test. They both address the same null hypothesis and degrees of freedom within for the degrees of freedom for the t-test, so n minus 2. And then you're going to your mean squared within as equal to your variance pooled. Your f-stat is going to equal to your t-stat squared, and your f of 1 degrees of freedom 2 alpha is equal to your t degrees of freedom of 1 minus alpha squared. So now into 3.4, your post hoc comparisons. So remember how we said ANOVA will tell us that at least one population mean differs, but doesn't tell us exactly which one differs, right? It doesn't delineate which is different. So we have to run post hoc comparisons that will help us determine which means are actually different from each other. Post hoc comparisons are pursued after the rejection of an ANOVA null to delineate differences. So if you were to go into SPSS, the two the book talks about are LDS methods and the Bonferroni method, which multiple comparison procedures are available in the SPSS window. LDS stands for least squared distance, and the Bonferroni methods are covered in the next session. These would be the 2 buttons you would click. As far as I know, Excel does not have these specific options to do these types of tests. So let's get into the least squared difference procedures. So you do after a significant ANOVAs, after a significant ANOVA to protect against the problem of multiple comparisons. Your hypothesis is, the null hypothesis is that your groups are going to equal, versus the alternative hypothesis that your groups are not going to equal. For each group, you use I and J. So you have a t-statistic. Your t-stat is going to equal to your x bar I minus x bar j over the standard error of x bar I minus x bar j, where the standard error of x bar I minus x bar j is equal to the mean squares within of 1 over the group ni plus 1 over n group j. And your degrees of freedom is degrees of freedom within, which is n minus k. Remember, once again, we're going to be using going over this information, but you do not have to know how to calculate stuff. This is just more or less after you have an ANOVA. These are different post hoc comparison tests you can run. So going a little quickly through this, because you don't need to know all the math, but just know the theory behind it. So if we take our PETS illustrative data, we're testing our null hypothesis of group mean 1 equaling mean 2 by hand. The other tests will be done by computer. If we were to do this for group 1, group 2, mean squares within, and plug in our values here, we get 3.362 for our standard error. So our t-stat is our x bar 1 minus x bar 2 over our standard error for those groups. Plug that in, we get negative 5.31 with degrees of freedom within equaling 4 to 2, and a p-value of 0.5039. So it's highly significant evidence of a difference. Plugging into SPSS, as you can see, what they're doing is they're taking your group 1 for I and groups 2 and 3 for J and comparing them against each other, right? So they're taking 1 versus 2, 1 versus 3, 2 versus 1, 2 versus 3, 3 versus 1, 3 versus 2, determining if there's significance between the 2 groups here. So you have your mean difference, standard error, significance, and 95% confidence interval. To calculate your confidence interval, you take 1 minus alpha at 100% for your confidence interval of mu I minus mu j, equaling this equation, which is fairly similar to the things we've been doing, except multiplying it by the mean squares within instead of well, this is the standard error. We've just been staying standard error, but this is how we calculate it. So here we go for a 95% confidence interval using the least squared method. Example comparison of group 1 to group 2. Plug our values in that we have for our averages for group 1, group 2, plus or minus our t-stat value of n minus k. That's where we get a 42. 1 minus alpha over 2.975, so 87 point, and then times by 87.793, multiply 1 over 15 plus 1 over 15, get these values, and then we can get our confidence interval of negative 24.6 to negative 11. Bonferroni procedure. So the Bonferroni procedure is instituted by multiplying the p-value from the least squared procedure by the number of the post hoc comparisons. So we have the same hypothesis set up. Our t-statistic is the same for the LSDS. Where we go is our p-value has to be different, because as you're running multiple comparisons, this is taking a much more conservative approach, I'd say, to it. The LDS method produces a p-value of 0.000039, two-tailed. Since there were 3 post hoc comparisons, you multiply that number by 3, and then you get your Bonferroni new p-value. So for a Bonferroni confidence interval, you let C represent the number of post hoc comparisons. So it depends on how many groups you have is how many comparisons you make. So this is comparing group 1 to group 2 for this confidence interval. As you can see, fairly similarly set up to the way we've been doing our confidence intervals. Plug our values in. You'll notice that the 1 minus alpha, instead of over 2, it's multiplied by our C here for the number of comparisons in the groups. So as you can see, this number has changed a little bit because we're multiplying by the number of groups here, so 2 groups. So it's over 4. Alpha over 4, 1 minus alpha over 4 is where we're getting this. And then we plug in our values and we get our confidence interval of negative 26.3 to negative 9.4. Once again, this is what SPSS would give you after you ran the groups. It's still comparing groups 1, 2, and 3 to the other groups in between, giving us our mean difference, our standard error, our significance level, and our confidence interval for each group being compared to each other. Just as a reminder, the Bonferroni adjustments for multiple comparisons avoids more type 1 errors than the LDS method, but makes more type 2 errors. Also, the Bonferroni adjusted p-value compensates for the problem of multiple comparisons. Before I go into 13.2, I just want to also just restate that, remember, once again, this video might be going fast. We're just going over information. We won't be going over everything, or none of the stuff will be on the exam. It's just good to know this information going forward. So the assumptions, the equal variance assumptions, so conditions for ANOVA. Remember, the sampling has to be independent, normal sampling distributions of means, and equal variance within the population groups. So let's focus on condition 3 since the other 2 have been covered. When we have equal variances, it's called homoscedasticity. Unequal variances is heteroscedasticity. Sorry, I might mess these up a couple times. Can't really say them very fast. So homoscedasticity allows us to pool groups of variances to form the mean squares within. So assessing equal variances. We could do graphical exploration. We can compare the spreads visually with side-by-side plots. We use descriptive statistics. If a group's standard deviation is more than twice that of another, you want to be on the alert for possible heteroscedasticity. Test variances. A statistical test can be applied. So the statistical test that can be applied is called Levene's test of variances. So we have our hypothesis, or now we're testing the hypothesis of the sigma here instead of the mean. And our test statistic is performed by a computer. The test statistic is a particular type of F-stat based on the rank transformed by deviations. You can see page 317 for more details. The p-value for the F-stat is converted, or the F-stat is converted to a p-value by the compilation computer interpretation of P is routine. Small p evidence against the null suggests heterosidacity. Wait a minute, that doesn't seem like that's the next slide. Yes, this is the next slide. Sorry. I don't know how that moved around on me. So figure 13.16, Levine's test for pets in the stress illustrated example. We state our null hypothesis and alternative hypothesis where at least one standard deviation or sigma differs. Here's the SPSS output below. Here we have an F-stat equal to 0.059 with 2 and 42 degrees of freedom respectively. And our P equals 0.943, which is very weak evidence against the null hypothesis, so we retain assumption of homocidacity. So, analyzing groups with unequal variances, use summary statistics and EDA methods to compare groups, where you want to remove outliers if appropriate, mathematical transform the data into compensate for heterosidacity. Example, a long right tail can be pulled with a log transform. And then you want to use robust non-parametric methods. So with that, I'm going to stop this video so I can do the next one and get into the introduction to non-parametric methods, where this slide basically shows the sample type, if the test is normal, if we're going to use a non-parametric test, and which test lines up to that. Alright, so I'm going to end this video here. See you in the next one.